Well, thank you, and thank you for attending my talk, and thanks to Lisa for inviting me for another talk. And thanks for the introduction, Doug. That's right, I infamously have become known as Shouting Guy. I hope some of the other accomplishments of my career are more interesting than that, but that's fine. It is quite an amusing video. How many people have seen that video, by the way, the shouting at... Okay, so most people in the room. So I am actually Shouting Guy. This talk, I'm going to talk about performance analysis methodology, in particular the use method. This is a new methodology that I've developed to help people find bottlenecks and errors on systems. And an article appeared in ACMQ this morning that I wrote covering the use method. So much of this presentation is based on that. I'm a lead performance engineer at Joyent. I work on performance tools. I've written many in the past. Some people might know me from tools like IOSnoop, which is installed by default on Mac OS X. I wrote the dtrace toolkit. I've written a lot of different performance tools. More recently, I've done visualizations such as heat maps for analysis and methodologies. I was Brendan at Sun, Oracle, and now Joyent. Just to mention what Joyent, my company, does, we're a high-performance cloud infrastructure. We do public and private clouds. We have OS virtualization for bare metal performance, which works fantastically well. We do have KVM for Linux guests, and we're the core developers of SmartOS and Node.js. Something that I guess isn't on the slide is that we have a lot of people who come from other providers and who are running other operating systems. And since we tell people we're the high performance, that's actually the tagline at the top of the Joyent website now, we're the high performance cloud infrastructure, many of our potential customers say, well, prove it. Make this operating system go faster, make my applications go faster. And I come from an enterprise world, and it's very different in the cloud world. People get to change very rapidly. And so in the enterprise world, you might have to go through a proof of concept. It can take days, it can take weeks. This can be all done in an hour in the cloud world. So the rubber meets the road very fast, and you have to prove that you can deliver performance very fast. And this is, now that I'm working on this in the cloud, I've been able to work on performance methodologies at an increased pace, much faster than I did in the enterprise world. At Lisa 10, I talked about performance visualizations. So that included latency heat maps, including crazy ones like the latency pterodactyl, which I still don't understand every single feature of, but understand most of them. And this year I'm talking about performance methodologies. I've been studying them quite a lot for an upcoming book, and this is the first time I've mentioned this publicly. Next year I have a book with Prentice Hall called Systems, Performance, Enterprise in the Cloud, and it's fantastic. I get to write a lot more about methodologies and tools and visualizations for both of those environments. And funnily enough, the primary operating system for this book will be Linux, and then Solaris-based operating systems are secondary, because that's especially in the cloud world, there's a lot of people running Linux. Although the methodologies are actually common, and the methodologies I'm talking about in this presentation, it doesn't actually matter if you're Linux or SmartOS or FreeBSD or Mac OS X, it's going to be the same methodology. So what I'll talk about, I'll start with a performance issue example, and then I'd like to go through 10 performance methodologies and anti-methodologies, and in particular focusing on the use method. And I put in the slide deck, the content is based on an article that just got released today, and I've also done a lot of research into methodologies for Prentice Hall. And I've also done a lot of research for methodologies. I'm teaching classes again. I used to teach classes many years ago in systems performance. I'm now doing that again, and actually teaching people, fix this problem, and here is a methodology you can follow, is when you get to find out whether it works or not. Because if the student can't fix the problem, in some ways it's not their fault, it's my fault for not giving them a good enough methodology to go to root cause quickly. And so I've been able to put a lot of these methodologies to the test by giving people simulated issues and seeing if they solve it. And being very pragmatic about and understanding that it's my fault if they can't solve it. I need to help develop these methodologies and provide that guidance. The content in this talk does have a focus on systems performance, but it's also applicable to applications. So to start with, as a performance issue, and this was one that happened recently, and it's also happened very similarly more than once. The database response time sometimes takes multiple seconds. Is the network dropping packets? The customer tested the network using traceroute and found that yes, indeed, the network was dropping some packets. So if you drop a packet, then you have a retransmit. If that happens during a query, that can add 1 second of latency or 3 seconds of latency. It depends on the retransmit interval. So this seems like a fair hypothesis. We have a performance support chain. We have people at the first level who look at the tickets and try and resolve them. We have at second level people who have expertise. I kind of end up with all the too hard issues that no one else can fix. At the first level, they ran traceroute, but they couldn't reproduce the issue. At the second level, they looked at the network and said it looked fine. And while they were logged into the systems, they checked CPUs as well. Now, the customer description didn't mention CPUs. The notion is, or the idea is, this is an ad hoc checklist that those support staff did because they've commonly hit issues of CPU, especially this is a cloud computing environment. And so while they're there, while they're logged into the systems, I'm going to check some other recent issues and see if it's any of them as well, even though the customer didn't mention them, because that proves successful. So they checked a few other things, like CPUs, said that looks okay. Doesn't actually look like there's an issue. And so now it's my turn. I could try network packet sniffing. Now I can run TCP dump or snoop, and I can capture every single packet that went on the wire and then analyze that. I can analyze that using Wireshark and various other tools, Ethereal. There is performance overhead during capture. That's the CPU cost of instrumentation and the storage cost of saving it. And also moving it around. If I'm putting it on a server and need to move it to my laptop for analysis, there's more network traffic I need to do. Also, try doing this on a very busy 10 gigabit network. You have very large files very quickly. It starts to become prohibitive. It's time-consuming to analyze. It's not real-time. I like doing it, and I'm good at doing it. I used to do this a lot in the past. Nowadays, I do a lot of dynamic tracing of the TCP/IP stack. Here, it's efficient. I can only trace the drop and retransmit paths. I have access to the kernel context, so it's not just what's on the wire. I can look at the TCP state. I can look at various counters that the kernel has in its brain that you don't see on the wire that might explain why connections have been problematic. A lot of those counters, by the way, they're exported via SNMP. So there's standard MIBs for these counters. Plus there's internal ones that you don't normally see. It's real time. So just as an example script, this is a dtrace script, TCP listen drop, and I can see which SYN packets were dropped. And the source IP address, the destination IP address, the timestamp. SYN packets get dropped when you reach the end of your TCP backlog, which is why we tune the thing. And that will happen if you have a burst of load. So I love doing this. I love going into the TCP/IP stack with dtrace and understanding things and solving problems. And so here's a customer who has an issue. I've got network packet drops. I have query latency. It comes onto my table, and I get to do this stuff, which is really fun. But instead, I began with a methodology. Instead of doing all the really fun stuff, let's do a methodology to check the system, check basic system health before I go down into the TCP/IP stack, because that's worthwhile. I used the use method, which I'll be covering in this talk, and in 5 minutes I found that the CPUs were okay, just like support had already found. The network was okay, just like we suspected. But memory was exhausted, and the system was paging. In Linux, you call this swapping. And the disks had periodic bursts of 100% utilization. These are serious issues. If the system's paging, and I could see that it was paging the application, that's likely to be your performance issue. They had been overlooked because the customer had talked about networking, and people had a target fixation on the networking issue. The customer was surprised by my analysis. Are you sure? But I had these drop packets. And I was able to then prove it using a different methodology, using a latency analysis. And so for latency analysis, on this particular system, I had microstate accounting and dynamic tracing available. So microstate accounting, I can look at the time the application was blocked doing anonymous page-ins, because there's good page-ins and there's bad page-ins. Anonymous page-ins are the bad ones. This means you've been paged out because you've exhausted memory. And so I can look at the time that the thread was blocked on this. This is not just some counter, this happened. Yes, you are actually blocked for 100 milliseconds on the anonymous page-in. This only happens because you've run out of memory. And so this is a very good way to confirm that that has hurt the application. And also for disk, I looked at the synchronous latency of the application to the file system interface, and there was 1,000 millisecond fsync calls, which were happening in application context. That's slower. So digging this stuff out took me about an hour, only because these are actually very common, running out of CPU and needing to, running out of memory and needing to look at anonymous page-ins, having disk issues and needing to quantify that. It's something I do very often, so I can get that done in about an hour, otherwise it'd take half a day. But it's different to the previous methodology. The use method, I can go through that in 5 minutes and just check just give you that first pass of system issues, and then I can use a deeper methodology like latency analysis to confirm it and to quantify it. So methodologies can help identify and root cause issues. Different methodologies can be used as needed. In this case, I used those two. It's a faster resolution of issues. It frees time for multiple teams. We often find that once you find the location of an issue, that means the other teams involved can go home. Normally, you have this performance crisis. We have the database team online, the sysadmin team online, the application developers online, the OS engineers online, which is usually myself. And once you find the location of it, the other teams can go home. And so having a faster resolution of issues, it's not just fixing the issue. It's about freeing up time for all the staff involved. And that's why quantifying is important, because you cut through this sort of political blame game. Once you quantify it, then you know for certain, and you can then go and it gives management the power to invest in fixing that solution, gives them the numbers they need. So performance methodologies, I normally give tool talks. I normally talk about performance analysis. I love it. I love using dynamic tracing and the existing tool set. This is why I co-authored Solaris Performance and Tools. But methodologies, it's not a tool. It's not a product. It's a procedure. It is a documentation. And it's a procedure that I can include in the slide deck. I put in the ACM article this morning. You can build tools to help. So I could build a tool to facilitate the use method and a tool to facilitate latency analysis. It could also be products. So if I'm purchasing monitoring solutions, that could be part of the product. It could give me a use method wizard. The audience for methodologies, for beginners, it provides a starting point. One of the hardest things with performance analysis is, where do I start? I have this issue. I know my environment is hugely complicated. I have databases and the application tier, and then the caching and load balancers and the storage arrays. There's a lot of components. I don't know where to start. I don't know what tool to begin running. So methodologies give you a starting point. For experts, it's useful as a reminder. I like the methodologies because I forget things, and I can use them to refresh my brain and to remind myself, yeah, I should stop this methodology. It's not working. I should try drill down analysis instead. I should try workload characterization instead. So for me, it's a reminder. For casual users, there are a lot of people in between. There are a lot of people who are, I'm doing web developing, performance is not my day job, but I need to know enough. I'm doing sysadmin, performance is not my day job, but I need to know enough. And so methodologies provide you a checklist. So something you can step through and let's just check that I've gone through the basics and found the egregious issues. Operating system performance circa 90s was metric orientated, where the vendor created metrics and performance tools, and the user developed methods to interpret the metrics. I did a lot of performance analysis in that culture. And the previous common methodologies focused on ad hoc checklists of common tuning tips, tool-based checklists, which seem to make more sense in some cases, where for every tool, you then say, these are the useful metrics, and this is how to interpret each metric, and these are the actionable items based on the interpretation. And there was another methodology, which was the study kernel internals and then develop your own. And it gives you a great understanding of the system you're trying to analyze, or study application internals, for that matter. But that takes a lot of time. There is a common problem to all of this, and that was vendors didn't always provide you the best metrics. And the metrics they provided were often incomplete. And it's very difficult as a consumer to have this epiphany that the operating system vendor or the application vendor who wrote this software, who knows it inside out, who has a bug database of all sorts of weird issues that I would barely understand a tenth of them. It's hard to imagine that they haven't given me the best metrics, that there's areas that are missing that they haven't included as part of the product. But this happens a lot. Operating systems now provide dynamic tracing. So you get to see anything, not just what the vendor gave you. I get to do that using dtrace a lot. Of course, dtrace is on Solaris-based operating systems, including SmartOS that we use. Oracle has been porting it to Linux, and they had an announcement a couple of days ago. They've pushed another release of their dtrace for Linux port. And it's not the only Linux port of dtrace, if you're interested in that side of things. But there's also other ways to get dynamic tracing as well. The hardest part about using dynamic tracing, whichever tool you use and whichever operating system you're on, the hardest part is knowing what questions to ask. With dynamic tracing, I can instrument every function in my application and every function in the kernel, which is probably 100,000 different things. What do I do with it? What script do I write? Methodologies pose the questions. And so the methodology will help you see, this is the question, this is the small question I need to answer. Now I can go and use dynamic tracing to answer that question, because that's part of my drill down analysis or latency analysis. I'm studying methodologies a lot more because of dynamic tracing. Previously, without it, it would have been much more of an academic exercise. It would have been a lot of effort that I could come up with these great latency analysis techniques and procedures, but no one could benefit from them because you didn't have any tools to do it. With dynamic tracing, you have that catch-all. If the existing tool set doesn't do it, you have some means to go and answer those questions. So the rise of methodologies, at least the rise of my analysis and study of methodologies, is very much related to dynamic tracing because it means it's a practical exercise. I'm able to do this much more in production, on real systems, and deliver results. So, going through 10 methodologies, starting with some anti-methodologies for comparison. The first one I've got is the blame someone else anti-method. And it works like this. So for each of these methodologies, I've enumerated them, which is great if you're a beginner. It gives you a series of steps to follow. Find a system or environment component you are not responsible for. Hypothesize that the issue is with that component. Redirect the issue to the responsible team. And when you're proven wrong, go back to step one. Anyone know any group or staff or support team that does this? This kind of sound familiar. I have a few hands going up. This is why I called it an anti-method. This is an anti-methodology. This is not scientific. Maybe it's the network. Can you check with the network team if they've had dropped packets or something? This is a very familiar thing. I know if you're a network administrator, you must get tired of hearing this. You must get tired of getting blamed without any sort of evidence. Maybe it is the network, but please have evidence. A colleague asked if I could make that methodology into a flowchart. It's like, all right, there's the flowchart. Please don't learn this methodology. This is not the point of the talk. It's here to recognize and to compare. So this is wasteful of other teams' resources. It's identifiable by a lack of data analysis, and in some cases, any data at all. In order to deal with it, ask for screenshots. If you're getting blamed for something, ask, show me the data that makes you think that there's a problem with the network. And you can take those screenshots to someone else for a second opinion. Say, would you conclude that there's a problem with the network based on this? Streetlight Anti-Method. For the Streetlight Anti-Method, you pick observability tools that are familiar, found on the internet, or found at random. You run them, and you look for obvious issues. It seems to be what a lot of people don't do. This is the absence of a methodology. I'm just trying to Google some things, look at Stack Overflow, let's try this, let's try that. I called it the Streetlight Anti-Method after an observational bias called the streetlight effect, and that follows a parable. A policeman sees a drunk looking under a streetlight and asks what he's looking for. The drunk says he's lost his keys. The policeman can't find them either and asks if he lost them under the streetlight. The drunk replies, no, but this is where the light is best. Again, might sound familiar. Some of the common cases where it comes up, when someone has a performance issue where they've just run ping. Why were you running ping? The performance issue you're describing is about the storage array. Why are you testing the network? Is ping familiar? Another one where it comes up is where the customer has been running top for a very long time. They've been running top for days and they haven't progressed past top. Now, I use top. Top's great and solves a class of issues, but I use it for a very short amount of time, and then I'm using various other tools to drill down further. So why are you still running top? The Streetlight Anti-Method is a tools-based approach. It is inefficient. It can take time before the right tool is found. It can be wasteful when investigating false positives. And sometimes, especially with, I guess the network administration teams are now getting very, very good at this, the ones I've worked with, when they get blamed for things, because people have run ping, because that's familiar. And so they can not waste their time so much by coming back and saying, no, it's not the network. We have monitoring in place. We can confirm that quickly. The Streetlight Anti-Method, probably the biggest problem is that it is incomplete. You're missing out on various issues that the tools aren't easily identifying, especially if the tools are difficult to find or learn. And of course, tools are incomplete or missing. And this goes back to, don't assume that the vendor has given you every single metric, because often the vendor has not. Now, I've been that vendor and I've worked in the performance groups, and there's always more that we can do. And there's always like vast areas that are just missing. It's like, we know we need to add counters to this area, and we just haven't done it yet. It's a ticket in the system. So incomplete. You might be missing out on things. The ad hoc checklist method. Now, this isn't quite an anti-method, because this can be useful. You have a series of steps, 1 to n. Run A, if B, do C. Each item can include which tool to run, how to interpret the output, and suggested actions. And you can cover common and recent issues. As a key example of this, Adrian Cockcroft's book, Sun Performance and Tuning, was influential. And on page 1, he had quick reference for common tuning tips, which had an ad hoc checklist which went through 11 items. And it's interesting because he put this on page 1. You open the book and it's like, let's go. It's time to look at disk bottlenecks and run ISTAT with 30-second intervals and look for more than 30% busy disks. And went through NFS response times and memory checks and other things. These ad hoc checklists are easy to follow. They can be fast. They give you a consistent check of all items. So if I am creating an ad hoc checklist, it's great because I get to put those nasty issues in there that I know people are struggling to find, and I get to make sure the list is complete. And it can be prescriptive. It can say, do this. If you see this, do that. Which for beginners it's taking you all the way from not knowing where to start to actually fixing the problem in the shortest amount of time possible. Which is why this can be pragmatic. This can be a process that an entire team of staff can follow to check a minimum set of issues and deliver a practical result. And I've seen this used successfully where you have a large organization says, I have this support team, they need to deal with some performance issues. They're not the performance experts, and they're not trying to be. Their expertise is with products and with other areas. But as part of their day job, they sometimes need to go through and do a quick pass of performance issue checks. And so they'll use these ad hoc checklists. The cons are probably pretty obvious. It's limited to the items on the list. It's point-in-time recommendations. It needs regular updates. And people follow these lists without really having an understanding of what they're doing. And that can be problematic as well. So the ad hoc checklist method, it has uses, it has pros, and I've included that as it is a very commonly used methodology. Problem statement method is the next one. This is used by support teams. It's when you first contact a vendor and you say, I've got an issue, often the support team will go through a series of questions. I've seen some companies will actually send you a form and say, you have to fill out the answers to these questions, and that gets put into the ticketing system. For example, for performance issues, the questions might be, question 1, what makes you think there is a performance problem? Question 2, has the system ever performed well? Ever. Question 3, what changed recently? And so on. This doesn't require running any tools. This is just asking the customer questions about the issue to see if we can solve it straight away before we engage the back-end engineering team. And often this is very effective. I've got some example answers here. What makes you think there is a performance problem? I saw 1,000 disk IOPS. I've had this a lot. Great, 1,000 disk IOPS. So what? Is that a problem? Did you have 10,000 before or 100 before? Disk IOPS, of course, these days in modern systems are frequently asynchronous to what the application is doing because of features like prefetch and write buffering. And you don't have a direct path between disk latency and the application latency on purpose because we've put a whole bunch of engineering into the stack to separate the two because disks are slow. So starting with disks as your problem statement is a bit questionable. And IOPS themselves, on previous rotational media, it could be sequential IOPS, it could be random IOPS. Fortunately, we're on flash media now, which don't have the sequential random issue, except for a tiny bit because of what the firmware does in the way it does address mapping. On flash memory, instead of random versus sequential, it's more, are you doing reads versus writes? And what's the size of them? Because if you actually do 10 megabyte I.O. versus 1 kilobyte I.O. or 4 kilobyte I.O., there is a millisecond difference there. So 1,000 disk IOPS, it's just not enough information. The question 2 was, has the system ever performed well? I've had this sometimes where the customer says, here's a performance issue. go solve it. And so I've rolled my sleeves up and I've dived in, I'm running all sorts of tools. And it's like, wow, this system is just terrible. There's performance issues everywhere. I can't imagine how this ever worked. And I'm trying to hypothesize, how did it break? How did it go from a working system to this complete mess that they've given me? Like, there's issues galore. And so I spend like a day or 2 days, and I go back to the customer, and I'm like, I just can't figure it out. I don't know how you got here. I don't know how you got into this mess. And they say, oh, it never worked. We just built it. It's never, ever worked. We just filed that ticket. We thought you'd figured it out. It's like, thanks. It would have been great to know that from the start. So yeah, has the system ever performed well? Good question to start with. What changed recently? That can be, we're on Slashdot, we're on Hacker News, we're on Reddit right now. And I've had many cases like this where, again, you're looking for like, how did the system break? And it's meta. The system didn't break. They're on Slashdot right now. And that's why there's so much load, and that's why you've got network drops, et cetera, et cetera. Important question to ask early on. And sometimes it's funny where the customer will argue and say, no, it's a problem with the operating system, or it's a problem with the applications. It's like, please check if you've had a spike of load. Like, what has happened? Because that's what it looks like. Can the performance degradation be expressed in terms of latency? That's a great one because you get to quantify it. So is query time 10% slower or 10 times slower? If you put that into the ticket, that might help you say it's a P1 ticket or a P5 ticket or whatever the scale system is. Does the problem affect other people or applications? Great question to ask. So yeah, my networking for this server is a bit odd. It's offline at the moment. So you spend a while, it's like, I can't connect to the server. Let's try some other, I can't connect to anything. Oh yeah, the whole network's down. So important question to ask, does it affect other people? And also, what is the environment? So whatever your environment is, it's a worthwhile exercise to go to the bug databases for all your components and search for the keyword performance. Just so you know, everything breaks. Everything has performance issues. From CPUs to firmware to databases, the operating system, the kernel, everything has performance issues. And performance issues get fixed. And if you are running a much, much older version of disk firmware or storage HBA firmware or the operating system kernel or the applications, there may be a large subset of performance issues, performance fixes you don't have. That's why we ask this early on. What's the environment? Often people are following the mantra, if it's not broken, don't fix it, which makes a lot of sense in some ways. Until it is broken. It's broken because the performance is now bad. And so let's look up the bug database. Yes, that's a known issue. Let's now do the fix. Let's now upgrade it. So the problem statement method, it's often used by support staff for collecting information and entering into a ticketing system. It can be used first before other methodologies. It's fast. It resolves a class of issues without further investigation. It has limited scope. We're not running tools and diving into the system or applications yet, but that's obvious. But it's a great first methodology to use. Scientific method. Some people, hands up if this is dead familiar. You taught this at school, just curious. Wow, lots of people. So you may already do this in your sleep. Basically, the whole room put their hands up. You may already do this in your sleep, so this might be nothing new. With a scientific method, question, hypothesis, prediction, test, and analysis. The way I was taught it, we spent a lot of time enumerating our assumptions and then going through them as well, which is also useful. For performance analysis, the test stage, in order to verify the hypothesis, you can have observation tests where you run a tool and read a metric, and you can have experimental tests where you change a tunable parameter, increase or decrease load. One thing that some of the best people in the industry I know at performance are good at is having a good balance between observational and experimental. So for me, it feels like these are my two hands when I'm operating on an issue. I get to observe things and I get to change things and then look at the effect of those changes. Some people get really, really good at one of these, but not the other one. And if you feel like you're fantastic at experimental, I can benchmark this and deduce all these wonderful things, like perform all these tests, then try looking at the observational toolset and learning them, and vice versa. Because they're both equally very, very useful. I've got some examples so you can see how this goes together, but this might be pretty obvious. So example A, observational. Question, what is causing slow database queries? Hypothesis, noisy neighbors, because we're on the cloud. They're performing disk I/O, and it's contending with my database disk I/O. My database is using the disks via the file system. So actually, it's my file system latency that's slow. It's slow because of noisy neighbors. Prediction, okay. This is going to be observational. If file system I/O latency is measured during a query, it will show that it's responsible for the slow queries. This is how we can measure it and actually put it to the test. If what you're saying is true, it's noisy neighbors and they're rattling the disks and they're slowing you down, that's going to manifest it up at the file system interface, and we can measure that and prove it. I do this a lot, actually, because it's a commonly blamed thing. Dynamic tracing of database file system latency as a ratio of query latency. For this example, it showed that it was less than 5% of time was in the file system. So for our analysis, we can say, well, it's not the file system or disks. You need to look at what the 95% of time was and analyze that. These days, we actually have, this is such a common issue, we put ZFS I/O throttling into SmartOS so that tenants, there's actually a way to throttle I/O between them. Example B, observational. Why is an app slower after moving it to a multiprocessor system? Hypothesis, it's NUMA effects. Remote memory I/O, CPU interconnect contention, less cache warmth, cross calls. All sorts of bad things happen when you start adding extra processors. It's a real feat that things scale as well as they do. It's so hard when you have to have cache coherency. So we're going to blame NUMA effects for the app being slower. For the observational prediction, there should be an increase in memory stall cycles and an increase in cycles per instruction and remote memory access. I can observe these indicators from the CPU performance counters, to test my hypothesis. The test can be using perf events or CPU stat. It takes a lot of time to do this stuff. You have to bring up the processor manuals and read the performance counters and figure it out. For that observational test, analysis consistent with predictions. And I just see this sometimes. This is a thing that does happen where the app is slower. Sometimes experimental can shed light on that much, much more quickly than reading those processor manuals. Same problem, but now I've got a different prediction. How about I disable the extra processors and see what happens? So my prediction is, because it's NUMA effects, if I disable the extra processors and just take it to a single socket system, then performance will be better. As a test, we disable CPUs on extra processors, and perf improves by 50%. So experimental test, quicker than the observational test. It's not definite, but it's another clue, it's more information for you to continue your analysis. I actually do this a lot. And it comes from the scientific method. It's one of those things where I am performing a deliberate test in order to check a hypothesis. Just turning off CPUs. Of course, actually offlining them from the operating system is okay, but they're still powered on to some extent, and you're still using the memory bus. So it's not the same as ripping the socket actually out, but it will give you a clue. Example D. This is another example to go through these quickly. Degraded file system performance as the file system cache grows. Well, why would file system performance get worse as the cache grows? It should get better. Hypothesis, file system metadata overheads relative to the record size. So the cache has data in units of records. It might be 8 kilobytes or 128 kilobytes or 1 kilobyte. So the more records you have, the more contention on various metadata to look after this cached information, such as hash tables. So my prediction is, if I make the record size, this is a real world one that I had in enterprise, where we're already using the max record size. And so we kind of assumed that this is the problem, but in order to test it, we couldn't improve performance. So we said, let's actually hurt performance as a means of proving it, because we'd already gone to the max record size. So let's progressively reduce the record size and make it worse and worse. Let's go to half it, quarter, eighth, 16th, and so on, and then plot that on a graph and see how, just visually see how much that relates to our hypothesis. And that actually, the results are consistent with the prediction, and that's how we figured, we got some information on that one. And this is back to the scientific method. The tests you think of aren't just always improving performance. You can hurt performance in order to test out a hypothesis. And the last one, experimental. Why did write throughput drop by 20%? Hypothesis, disk vibration caused by a data center alarm. Prediction, any loud noise will reduce throughput. How would you test that? So let's just shout at the disks, and then measuring latency as a heat map, and it coincided. So maybe it doesn't look scientific, but in some ways you could think of it as scientific. Performing a deliberate test, and this is actually why I was doing it, because I was benchmarking and my throughput went down, and I wanted to have a good benchmark. It's like, well, I don't want to have 20% off the table. I need to resolve it and figure out why. And I checked everything. It's like, what could it be? What else could it be? Rotational disks. We had a data center alarm. Maybe it's vibration. I didn't have test equipment to reproduce noise, so I just used my voice. Scientific method. Pros, good balance of theory and data. Generic methodology, works for anything. Encourages thought and develops understanding. Cons, the hypothesis requires expertise, and it's time-consuming. It's more suited for harder issues. It does take a while to get through all of this. Workload Characterization Method. So this one's great, and it's another methodology you can follow. It's looking at the input to the system or the input to the target. We're not going to look at the resulting performance. We're just going to look at the input provided. So that could be, who is causing the load? What's the process ID, user ID, IP address? Why is the load being called? What's the code path? What is the load? What's the IOPS, the throughput, the type? Read or write, synchronous or asynchronous, file system I/O. And how is the load changing over time? As an example, I blogged this one. We had a customer with a system log checker, which was much slower after the system upgrade. And so I like to begin with workload analysis fairly early on when I'm looking at issues. And grep was on CPU for 8 minutes. And it was a small file. And so that's the who. So why was grep on CPU for 8 minutes? Like I'm not going to go straight to the performance of how grep's working internally, just the high-level questions. Why? Why are you doing this? It was doing UTF-8 encoding because lang was set to n_bar us.utf8. And setting lang equals C made it 2,000 times faster. So I didn't need to go down to the resulting details of performance. It's just the high level. What is being asked of the system? What is the input provided? The input in this case was grep was spending all its time doing UTF-8 encoding when it didn't need to. It was just grepping a log file for the word alert. So workload characterization method, it's great for issues of load. And the best performance wins are from eliminating unnecessary work. So I'm trying to, when I have time, put the recent performance wins on my blog so people get to see what we're doing. And you'll see that the big ones, the like 2x, 20x, 2000x, they're usually eliminating unnecessary work. This is not some tunable parameter like, oh, I need to set TCP buffer size or whatnot. It's that I did workload characterization, I found out something dumb was running, and we just turned it off. And now the system is much faster. Don't assume you know what the workload is. Characterize. That's a bit of a problem. Convincing people that I need to perform this methodology can be challenging. I've had cases where I'm doing performance consulting and I'm telling customers, disks look really busy. Let me characterize who's using them, what processes are accessing the disks. And they say, don't do that. It's a waste of time. We know what process is accessing the disks. It's an Oracle database. Oracle's accessing the disks. It's like, no, you're assuming. That's your assumption. Let me check, because we don't actually know that. And sometimes I have to really fight this. Please let me check. Please let me check. And so often you find, actually, the person that's running the disks, it's some research project you left running and you forgot about. It fires out of cron and does some sort of archiving to some other system every day. And you forgot about it because that project just died. So characterize the workload. Find out what's actually happening. The drill-down analysis method. This is another one that's workload characterization and drill-down analysis are somewhat in common use. With drill-down analysis, you start at the highest level, you examine the next level details, pick the most interesting breakdown or direction to go, and keep going. I wrote an example in Fast Performance and Tools with Jim Marron and Richard McDougall, where we just had 3 steps. Monitoring at the highest for environment-wide and identifying or alerting when systems have issues, and then identification for, given a system with an issue, looking at the resources and looking for bottlenecks and high-level issues. And then analysis where we drill down and down and down to the root cause or causes. The analysis stage was previously limited to the given toolset, though, because this is thought about prior to dynamic tracing. With dynamic tracing, we get to drill down a lot further. And just to give you an example of that, here's a kernel diagram, the IO stack diagram for, say, ZFS. A lot of these components might be very familiar. Drill down analysis, let's go top down and find out where the issue is. Let's say we have a suspected file system latency issue. Using dtrace, and I've got all these examples online, but just to illustrate what drill down analysis can look like, at the top level, MySQL PDFS latency looks at file system latency within MySQL, so that we knew that MySQL was hurt by file system latency. Then we go to the system call interface and check that the system calls, reads and writes, they too have the same latency. Then we can go into VFS. I've got scripts for that. We can go into, there's a neat place in between VFS and ZFS where I can I can go into ZIO slur, I can do sparse sync, ZIO snoop, go into ZFS. Block device interface, that's where IOStat normally runs. I've got lots more scripts for there. And then go down to the device drivers itself. It will find the problem. You will go all the way down to metal in search of where the latency is coming from, where the performance issue is coming from. It can take a lot of time, but that's the notion. This diagram here, so all these scripts are public. I put them in the dtrace book. Picture a similar diagram for your application internals. So you have, you want the functional diagram of how things fit together, or the layers, and then you want to drill down. An ideal place to start at the top is, what is the operation that you're doing, and what's its subcomponents and its subcomponents and subcomponents, and drill down until it's obvious, until you, I hit a point where I'm just blocked on this mutex for 90% of the time. I've got mutex contention. I've got a scalability problem. So you're moving from higher level to lower level details based on the findings. So I might stop because I've already found it. I might pick a different direction based on what I found. The pros, you will identify the root causes. The cons, it can be very time consuming to go through all of that. Latency analysis. Latency is the measure of time. So the term gets used a little bit differently. In network in the world of networking, sometimes latency refers to just the connection establishment time. So we say the latency for this website, and you've got the connection establishment, and then you have data transfer, and that's something else. In other areas, we use the term latency to mean everything, to mean the entire I/O operation. So it gets a bit confusing. So sometimes you'll hear people, when the word latency comes up, it's from what to what, so that I know what exact thing you're talking about. So latency matters because when you measure latency, you can measure it as a synchronous component of why your application is blocked when it's servicing a request. And that's also your operation time. Step 2, divide that latency into logical synchronous components. Continue division until latency origin is identified. And as a bonus step, you can quantify the estimated speed up if the problem is fixed. So if, for example, I've got my MySQL query latency, and I break it up into CPU time, join time, row search time, and then file system I/O time, and I find out that the file system I/O time is 90% of the query time, and I eliminate 90%, I can estimate the speed up and say speed up should be 10x. If you're doing this for a multi-threaded operation that's run in parallel, there's Amdahl's law of scalability, which helps you do the calculation based on the limiting factor. Just as an example of that, I read this for a customer where they wanted to log queries slower than 100 milliseconds, and so I printed out the query time and the sum of the file system I/O and the file system I/O count. So I had a little bit more information. We can identify if it was just one slow I/O or if it was a bunch of... there's two types of problems when you're talking to the file system. Either you have some outliers, some really slow I/O, or you're just doing too much. Sometimes the I/O is fast, but you're doing 10,000 I/O in a query. Don't do 10,000 I/O in a query. Just buffer that in the database. So this is why I put an extra column at the end of how many file system I/O. And so this is the information they needed for every single slow query, they can then identify, is it the file system or is it not? And if it's not, then it's in the database. And I can also add the column for CPU time and other database components. For latency analysis, you can do a drill down. Like the previous CFS examples, many of them were latency-based. You can do a latency binary search. So I might say my operation latency is A. I measure A. I then measure synchronous components B and C. If B is greater than C, keep analyzing B. Otherwise, analyze C. So I'm just breaking something up, and then I'm doing a binary search until it's obvious, until I get to that point where it's like, oh, it's a slow disk, or it is a mutex lock, or it is I'm blocked on CPU scheduler latency, or whatever it is. Another approach is spot the outlier from multiple layers. If I can measure latency at multiple layers, and the thing that is the performance problem is sometimes I have 1,500 millisecond I/O. It's like, okay, 1,500 milliseconds. It's nice that it's like between 1,000 and 2,000. If I measure latency from multiple places, I can almost use that as a unique key and say, oh, I see at the disk level 15, 12 milliseconds. I see at the VFS level 15, 60 milliseconds. I see at the application level 15, 90 milliseconds. These are probably the same thing. I didn't have to connect the dots that much. I'm just measuring the outliers from multiple places, and I'm just correlating them that way. There's another type of latency analysis. Just to give you an idea of yes, it's doable. This script I wrote just as a demonstration was ZFS stack latency, and it did a latency distribution of all layers from the interface to ZFS down to the disk driver. And so this is ZFS reads, and I can see the bulk of them. This is nanoseconds on the left and the count on the right. The bulk of them are pretty fast, 2 to 16 microseconds. ZFS writes, getting into ZFS itself, ZIO wait time. Now I've got an outlier at the bottom at 200 milliseconds. ZIO VDEV IO done. It's there now. I've got some other slower I/O included, which didn't bubble up to the application layer, which is interesting because sometimes you look at the disks and you panic about those latency outliers, but they're asynchronous. They weren't exposed at the read and write layer. And so I can go right down to the VDEVs and the block device interface and the SCSI interface and mega SAS for the device driver and correlate the latency distribution at every layer down to the disk driver and try and understand where's the latency coming from, is the latency bubbling its way all the way up the stack. So that's just a very brief example of drilling down for latency analysis. So latency matters. Similar pros and cons to drill down analysis. It's very time consuming, but you can approach solving every issue with latency analysis. This is the master methodology that ultimately probably can solve everything, but it can take a lot of time. Carrie Millsap has developed this with method R. He initially did that for Oracle databases, but it's applicable for anything. And that's an example of latency analysis. The use method. So this is the methodology that I developed a while ago when I was teaching classes to help my students solve problems effectively, something that they could learn and quickly identify the common bottlenecks and errors. I've used it a lot in enterprise and more recently in cloud. And recently I was inspired to actually write it up and share it so that people can follow it. It's very simple like the other ones. For every resource, check utilization, saturation, and errors. Fits on a slide. Utilization, it is either the time the resource was busy or it's the degree it was used based on the type of resource. Saturation is the degree of queued extra work, and errors is any error for that resource. I've got a picture here just to illustrate it. If this looks a bit like queuing theory, that's fine. Very, very similar ideas related to queuing theory, where we're looking at an input to a system that can queue, and that's saturation. And queuing theory also has ways of studying utilization in detail. And then I'm also interested in errors. As a flowchart, choose a resource, check errors, utilization, and saturation. You can check errors first, actually, because they are often easier to interpret, and it gets them off the table before you get into utilization and deeper saturation analysis. For errors, they're easy to interpret because often it's just the error counter. So, oh, your disks have hard errors, that's bad, replace the disks. Rather than at what level is utilization a problem, and at to what degree is saturation hurting. For hardware resources, you want to check everything. CPUs, main memory, network interfaces, storage devices, controllers, and interconnects. A great way to find them all is to find or locate the server functional diagram. Vendor or hardware teams have these. So when I was at Sun Microsystems, there is a team, or was a team that actually built the servers, and they had the blueprints down to metal of how they were all manufactured. Had fantastic functional diagrams of this is the memory components, and these are the buses they talk on, and CPUs. And so you might have to do a bit of digging to find server functional diagrams, but they're fantastic when you get them, because the diagram itself is a checklist. So I've just drawn a very simple generic example. And you can follow these diagrams by looking for the data path. Where does data go? This example here is I just drew like a two-socket example, which has a I/O bridge and then an expanded interconnect, I/O controllers and network controllers, a bit like Intel frontside bus. So yeah, I would want to check everything. Every box in the data path, and every bus. I want to check the memory bus. I want to check the CPU interconnect, the I/O bus, the expanded interconnect, and the interface transports. The definition of utilization depends on the resource type. So I mentioned this, but I/O resources, disks, utilization is the time they were busy. I can spend a lot of time talking about how blurry that can be for some types. which might be obvious. So especially if the disk device is a storage array controller, well, it says it's 90% busy, but it has many disks, many of which are idle, and so it can accept a lot more work than you may assume based on 90%. So we work with what we've got. Utilization is time the component was busy, and try to get down to the smallest individual component so that that value is more meaningful. Capacity resource, such as main memory, here utilization is the space consumed. Storage devices can act as both, because you can fill them up in terms of capacity, and they can get busy because they're doing work. Utilization, to interpret this, 100% is usually a bottleneck once you get down to the component, because now things queue. And if it doesn't go below 100% utilization, things will queue, and you have exponential growth. 60+% is often a bottleneck for I/O resources, especially when higher priority work cannot preempt them. And so CPUs, for example, do preemption, and so high priority work doesn't really suffer under high utilization because it gets to run. Disks, however, like mechanical disks, once you've sent those commands to the device, and once mechanical things are moving, you can't interrupt it. And so once you get beyond 60% utilization, the tail of the queue starts to hurt and latency grows. You can model this using queuing theory, and so you can see the graph of how latency grows for the different utilization levels. Beware of time intervals. 60% utilized sounds like it might be fine. If that's over 5 minutes, it might mean 100% utilized for 3 minutes and then idle. The smaller the time interval is better. And I've done some experimentation with ways of going beneath 1 second. And so if you're interested in that, look up sub-second offset heat maps, where this takes it down to basically an analog signal, so there is no arbitrary average. Utilization is best examined per device. For saturation, any sustained non-zero value adds latency, and errors should be obvious in terms of interpreting them. For some examples, so think about how you would measure these. CPU utilization, memory utilization, network interface utilization. With the use method, you come up with a checklist of about 30 or 40 of these items. So for every resource, those 3 metrics. It doesn't fit on the slide, but I've got some examples here. CPU utilization, well, that's actually pretty well available, commonly available in operating systems as CPU utilization, even though it kind of encompasses both memory, bus, I/O, and CPU instructions. CPU saturation, well, scheduler latency or run queue length, both those metrics work there. Memory utilization of available memory. Memory saturation, once you exhaust main memory, you'll be doing paging or swapping, so you can use them as metrics to identify it. Network interface utilization. Do your read, receive, and transmit throughput divided by bandwidth. For a lot of interfaces, you need to check both because both ports can work in full duplex. Storage device I/O, and I've got examples there as well. Those ones are pretty easy. For some harder examples, CPU errors. How do you currently check for CPU errors? What about network saturation, when you've actually put too much network to the device, sent too much network to the interface, or it's trying to receive too much? Storage controller utilization for the controller itself, that's a component. CPU interconnect utilization. As an example of a CPU error, a correctable CPU cache, like an ECC event, error correctable code, you could consider that a CPU error, a type of CPU error. I was once benchmarking a system where throughput dropped by 10% during the benchmark, and I couldn't figure out why for an hour, and I stupidly didn't use my own checklist, but it was a CPU had been predictively offlined by the Solaris FMA, fault management architecture, and the benchmark just kept running. I had no idea. It's like, why did performance go down a little bit? And it was because it offlined one CPU out of 16 because it had too many correctable ECC error events. I was on a prototype Intel processor, and we were expecting some issues. Network saturation. Solaris had this thing called no-cam puts, but whatever metric you can figure out there. You can also have some idea out of the TCP level if you've driven the network too much, out of the TCP counters, retransmits and what have you, and drops. Storage control utilization. Actually, you can figure that out by looking at active versus max controller IOPS and throughput. And sometimes by just adding, I know these disks are on this controller, and I know the throughput to the disks, therefore I know the throughput to the controller. And you can kind of figure it out that way. CPU interconnect utilization, that's when things get hard. So per port throughput on max bandwidth, and that's using CPU performance counters. The same for memory interconnect and I/O interconnect metrics. You can also do some software resources. So mutex locks, thread pools, consider possible use metrics for each. So how would I define a mutex being utilized? Well, you could define it as the percentage of time it was held. That might work. That might be useful. What about, and like once that mutex is getting held approaching 90%, then you can predict you're about to have a scalability issue. What about saturation for mutexes? Well, that could be the spins for adaptive mutexes. That might give you a counter for saturation. What about errors for mutexes? I'm sure there's error code you get from mutex acquire or mutex try lock or whatever. So again, for software components, try for the components to be as small as possible and to be single-threaded, but you may find use method metrics are very useful for quickly checking them and adding them to your checklist. The use method process begins with the questions you actually want answered. Begins with the resources, hardware and software, and then picks 3 metrics to characterize them. It may reveal missing metrics. So metrics you don't have, they are now your known unknowns. Previously, they were your unknown unknowns. It's much better to have known unknowns. And in performance, there's always a lot of unknown unknowns. It's like when we deploy this in production, like I don't know what it's going to hit yet. We'll find that as we hit it. Methodologies can help reveal them, which is great. I feel that the older I get, the more experience I get, I know less about performance because more of the unknown unknowns have become known unknowns. It's like the more you know, the more you actually don't know. It actually starts to become depressing. So yeah, there's a lot I don't know. More tools can be installed and developed to help. Please no more top variants. There's a lot of fancy like top with colors and this and that, and it's the same metrics. I want top that does interconnect utilization or bus utilization and saturation. Give me a bus top or bus stop. That's what I want. I don't want these colored tops, and it's not. I mean, people are doing great work and they're innovating. They're giving these incremental improvements, but I want these sort of metrics. I've put some example use-derived checklists on my blog, and this wouldn't fit in the slide deck at all, but I go through the sort of tools that you can use to figure out each of these metrics for Linux and for Illumos or SmartOS, which are Solaris-derived operating systems. To be thorough, you will need to use CPU performance counters. Who has used CPU performance counters? Hands up if you, they're sometimes called monitoring counters or other stuff. I've got like 10 people, it's pretty good. It's probably the most I've had in a room. That's great, you're in the right talk. Dynamic tracing, who's used dynamic tracing in any form? Doesn't matter. Wow, we have like more than half. We've got like 60, 70%. Great. Just out of my own interest, is that dtrace or is it something else? Hands up if that was dtrace. Okay, basically almost the same number of hands. Okay. Great that we're now approaching critical mass where almost everyone has used dtrace. So more hands, I hope next time I talk in front of a conference, more hands will go for CPU performance counters because there is a class of problems you do need to use them for. Like dynamic tracing and dtrace is great, but they are required as well. As an example of the sort of things you can do, here's a system I worked on previously. it was AMD hypertransport. I've got, for example, here's CPU socket 0. It has 3 hypertransport ports that connects it to the I/O MCP55 for the PCIe devices. HT0 connected to socket 1, HT2 connected to socket 2. Wouldn't it be great if I knew the utilization for all of those hypertransport links? And so I used CPU performance counters and wrote this thing called AMD 64HT CPU, and that's the decoder matrix. But it shows me the throughput for each of those links. And I did this previously at Sun and found out that our storage system was limited by CPU interconnect utilization on hypertransport 1, and we went to hypertransport 3, and the performance improvement was between 25% and 75%, depending on the workload, and it was just upgrading the hypertransport. And this would have forever remained an unknown unknown had I not had the impetus to go and check it out. So, although, if you think that's exciting, I should go run that tool. Probably doesn't work. You probably need to maintain it. The problem with CPU performance counters is that you need to spend quality time with the processor manuals, like hands up if that looks familiar. Oh, yeah. So now we have a few hands going up slowly. Yeah, this is like a 1,000-page book, and it's a lot of, it generally takes days. If you have a CPC problem, this is currently the state of affairs. If you have a CPC problem you need solved, it's probably going to take you like a day or two just to figure out the metrics you need. Life's getting better with PAPI, because one of the problems with the CPC counters is that they're model or platform specific, but PAPI is giving us generic counters. For the use method, products can also be developed to help. So at Joyent, we had cloud analytics, and that has metrics to support use. And so here is utilization as a heat map, and this is cloud-wide, and every CPU on the cloud, which is thousands of CPUs, are drawn as a point, and the more that fall into that same latency range, the darker the color. And the line at the top means there's some CPUs running at 100% utilization, so I can click on them and go straight to the host name. And so that's just an example of putting use method-related metrics into a product. Hopefully I'll see this in other products. I know there's a lot of performance monitoring products out there, and if you are developing a performance monitoring product, you could add a use method wizard, and you can refer to this talk, and provide utilization, saturation, and errors for all the components. It's okay that a bunch of them are going to be question marks because there's no easy way to get them. That's bringing things from unknown unknowns into known unknowns. And if you pay for a monitoring product, you can also ask for it and say, some of the monitoring products out there, like I know a lot of the companies who are developing them, they're doing fantastic work at monitoring multiple systems across the cloud. They have these great interfaces. It's like they definitely have the engineering power to take on hard problems. So this would be a great problem for them to take on, is to give this set of metrics. So the use method, it's a resource-based approach. It has pros and cons. It's complete because it will check for bottlenecks and errors. It is not limited in scope by your current tool set. I talked about unknown unknowns. And it's also efficient because if you were just to step over resources normally, some resources have hundreds of metrics and some have a few. This gives you just 3. This is what we're going to do. We're going to do a quick check of just 3 of them all as that first scan to see if there's anything egregious, and then you can use other methodologies. It's limited to a class of issues. So there's a whole heap of issues the use method won't solve. It is just one methodology in your tool set. And it's one that you use early on. The last methodology I want to mention quickly, I'm still developing this. I was teaching some classes recently in performance and telling students, well, this is how you solve this problem. And the students are saying, that should be a methodology. It's like, okay, this will be a methodology. I've called it the stack profile method. And like it works because this is how they're solving the problems. And it's how I solve many problems. And to go through this quickly, you profile thread stack traces either on or off CPU, and you then coalesce the stack traces, and you study them bottom up. It's different from what things currently do because I'm interested in stacks both on CPU and off CPU. There are a bunch of tools already that do stack sampling of on-CPU stacks like perf and oprofile and dtrace. And actually, there's a whole bunch of tools that do profiling by instrumentation, and they slow your target down by like 10x or 30x. I didn't even put them on the slide. At very least, I'm talking about sampling so that you can do this in production and have an idea of where CPU is being consumed. But for the stack profile method, I'm doing it for off-CPU as well, not just on-CPU. For every thread, I want the on-CPU profile and the off-CPU profile. It's not commonly profiled, and it's not commonly profiled to some degree, I guess, because of how these tools are normally built. They're built on sampling the program counter, and they're pinning the thread and doing interrupt profiling. With static or dynamic tracing, you can't actually sample what's off CPU, but what you can do is you can trace the stack trace. You can do the timestamp from when the kernel puts something off CPU to when it puts it back on, and that basically answers the same question. I previously called this off-CPU performance analysis. And so you examine both. I put a couple of dtrace one-liners in there just to show a tool like dtrace can do both of these, although it is kind of different. So there's sampling what's on CPU for the user stacks, and then that's tracing what's off CPU. The first one gives you sample counts, and the second one gives you nanosecond timestamps. But the sum of both of them is the stack profile method, is everything my thread does. I want to know why it's on CPU and why it's off CPU. If you haven't seen stacks much, that's what a stack looks like. And why we care about it, when we're studying it bottom up, it really gives you an idea of why something was happening. So this is a MySQL stack, and I can go through this and say, oh, it's handle one connection, dispatch command, execute command. It's a select. Now it's doing a join. Now it's doing myism, and now it's in key cache read. So this really explains why I was on CPU right now, or why I was off CPU right now. Although it requires a bit of familiarity with the code, a bit of time to study that. A big problem with stack profiling is that you can have a lot of stacks, just too much data to process. This is 60 seconds of MySQL on CPU, and this is already aggregated. This is frequency counting the stacks. So this isn't all the samples. This is already doing a first pass at trying to aggregate it down, and it's 27,000 stacks. That's the size of one stack. So at the command line, it's like, this doesn't work anymore. This is why I'm doing flame graphs. Has anyone used flame graphs yet? No one. Wow, a new audience. So in some communities, these are starting to become really popular, such as in Node.js. With flame graphs, I put it on GitHub. Whatever, you can take profile data. I don't care what it is, dtrace or perf events or whatever it is. Someone recently did it for Mac OS X instruments. And you can feed that profile data into a very simple Perl program I wrote that spits out a SVIG. And what it does is it coalesces the stacks so that I can then move the mouse. It's interactive, and I can move the mouse bottom up. And it'll give me the percentage of time for each of those layers so I can quickly quantify why I was on CPU. And I also did this for off CPU. So I can mouse up and say, oh, I'm 31% in here, I'm 20% in here. So from bottom up, those are my stacks. It's my stack population. The x-axis is population. It is not time. It's not the passage of time. And the y-axis is stack depth. The color is just random to make it easier to follow. And it's proved hugely successful. So perf events, if you're familiar with that from Linux, they have this. They have a couple of ways to do it. They have like a tree way of coalescing things up, and they have interactive mode. So just as an example tool set of putting that together for the stack profile method, I detrace on CPU and off CPU. I then coalesce it with flame graphs, and then I study it. And then I understand exactly why things were, exactly the breakdown of thread time. The pros, it can identify a wide range of issues, and it can identify it very quickly. The cons, it doesn't identify dependencies if my thread is blocked on something else. And if stacks aren't obvious, it can be time-consuming to browse code. And in some cases, you don't have access to the code. In some cases, there may be a terms and conditions you're not even supposed to. They might hopefully they don't confuse this with reverse engineering. It's not, it's profiling. But in some cases, you don't have access to the code, and so it's kind of hard to do. Not impossible, it might be obvious. Programmers tend to pick nice function names. So those are 10 methodologies very quickly, with a focus on the use method. The ordering, I start with the problem statement method, then the use method, and then deeper methodologies. That's just a suggested ordering. Some final remarks. Methodologies should solve issues quickly. And that's why we're here. We're here to solve issues. It's not about having fun going through checklists or whatever. It's about solving things. They shouldn't mislead or confuse, and they should be easily learned by others. And I said, they don't need to be followed strictly. They're a means to an end. You might actually incorporate stuff from multiple methodologies, and that works for you, and that's fine. I'm learning this because I'm teaching them to others, and that was the inspiration for the use method and the stack profile method, and I should be doing more classes in 2013 on performance. References, methodology origins, and that's methodologies, performance analysis methodologies. Thank you for attending. I think we've got 10 minutes of question time. Just on time. So I will put these slides on SlideShare like as soon as I can, and the USENIX people will get a copy as well. So these won't be hard to find. If you follow that Twitter handle, I'll tell you where they are.
Hi, Doug Hughes, DESHAR Research. I have a question on behalf of our scribe who's taking notes for everything. So, Mark Chirini, and he would like to know what sort of approach do you do when you don't have direct access to a lot of these resources? For instance, if you have something running in the Amazon cloud where a lot of the assumptions about access to things may not apply.
Right, and so in cases where you don't have access to the resources, to start with, the methodology brings them from unknown unknowns into known unknowns. And it's important because when you have that critical issue, at least you know what you don't know. At least you can then, it gives you the impetus to study that more. For example, for resources on the Amazon cloud, I can't go into the disk I/O stack, but I can stop at the syscall interface because I can't go, actually I can go into my, because it's doing virtualization, I can go into its stack, but I can't look at the back-end resources. So what I try to do is I measure latency as close as possible. I drill down as far as I can, and then quantify that do latency analysis, quantify that as a component of the response time, so that I can say, yes, I've confirmed that your back-end latency at Amazon is hurting my application, and I measured that. And I did that recently. OmniTI have they've got a version on the Amazon cloud. Theo's doing a talk later today, where I got to use dtrace, and I got to, the ZFS stack I showed earlier, I got to do all of that on the Amazon cloud. And latency outliers were terrible. It was the first time I got to see it with dtrace, but I can at least get to the point where I have a very rich set of metrics. Now, in terms of utilization, saturation, and errors, you don't have direct access to the devices because a lot of it's virtualized. What I would suggest doing is asking Amazon to give you a API means to get those errors to the raw devices. I don't know how receptive they would be. At least this is what we do at Joyent, is for the stuff you can't get to directly from within the zone, you should at least have an API means to get to them. And especially because the use method checklist it benefits both parties, because you will file fewer tickets if you have access to the information, and you'll be happier and we'll be happier because we'll have more time. So I think you can make a strong case to say, I want to follow the use method checklist. What can you give me in the instance, and if you can't, give it to me from the API.
Thank you.
Hi, my name is Karen Bruner, and I'm from Yahoo. And I have a question, especially for the latency analysis method.
Sure.
How useful is that if you don't have anything resembling benchmarks, especially if you're in a very heterogeneous environment, as for hardware, OS version, applications running? Do you need benchmarks?
Yes.
How do you work around not having them?
So benchmarks can be useful because you can apply known load, at least what you think is known load. I tend to hard code my own benchmarks so that it is known. But with latency analysis, I'm doing breakdowns that should be applicable regardless of the operating system or regardless of the software versions or the environment that it's deployed. And for latency analysis, when I was doing things like I was expressing file system latency in terms of MySQL query, if you start doing that too much using dtrace or dynamic tracing, that should be embedded in the product. That's when you should talk to the developers and say, look, I have to use dtrace too much. Can you please just add the counters? Because it will be even less overhead if it does it for free and easier for you to access and can be part of their analysis tool. So yeah, I don't think a lack of benchmarking is a problem. How do you tackle an environment? So a related question might be, my application behaves differently because it's used in different ways across my company. And I can't, latency of 100 milliseconds for this department means something else for another department. It's totally different. For those, you can look at how does latency match an SLA? How does latency impact the customer response? And again, if you can quantify it in terms of the customer response, I think you'll find that it works regardless of which role it's employed in.
Okay, thank you.
Thanks. Any other questions? Okay, great. Well, thank you for attending, and follow my Twitter handle, and I'll post the slides. And you can meet me. And also at the front, I've got Deirdre from Joyent, who does the Illumos community management. We've got some Joyent stickers and SmartOS stickers and Node stickers. I think we've got some T-shirts as well. You might be able to hit Deirdre for as well. So thanks for attending.